Section 4.6, Logarithmic and Exponential Equations. So the first thing is, just as a reminder, here are the properties of logs. Then when we're trying to solve log equations, the first thing is that we have what's called the logarithmic equality property. And in general, that just says that if you have two logarithms set equal to each other with matching bases, then you can set their arguments equal to each other. And so specifically, the arguments are m and n. Anything that goes into a logarithm, that's the argument. A logarithmic equation is an equation in which the variable is in the argument of the logarithm. So how do we solve those type of logarithmic equations? Well, first we're going to combine logs by using the logarithmic properties that we just showed. Then we want to isolate the log. Then, unless you can use the property of logarithmic equality, in which case you can drop the logs and just work on the arguments. Otherwise, you're going to rewrite the equation using the definition or in exponential form. Then we need to solve for the variable regardless of whichever property we do. Finally, you need to check for extraneous solutions. Recall the domain of a logarithm is greater than 0. That is, you can only have an argument that is positive going into a logarithm, so you need to check for this. So if we want to solve the following logarithmic equations, if we have log base 4 of x plus 2 is equal to log base 4 of 8, notice that I have a single logarithm, and our bases match, so I can just use the property of equality, that is, x plus 2 is equal to 8. Then solve minus 2 minus 2, x is equal to 6. Then we need to confirm that if I plug 6 into any logarithms that I started with, I'm only going to have positive arguments. Plug it in here, 6 plus 2 is 8, log base 4 of 8 is perfectly fine, and so that's our solution. Here we have 1/3 log base 9 of x is equal to 2 log base 9 of 5. Well, first off, we need to get the logarithms to be a single logarithm equal to a single logarithm if possible. And so I see that this 1/3 on the outside and this 2 on the outside, those can become powers of the arguments. And so that becomes log base 9 of x raised to the 1/3 power is equal to log base 9 of 5 squared. Well, then notice that I have a single logarithm equal to a single logarithm with matching bases. That is, I can now use the property of equality. X to the 1/3 is equal to 5 squared. X to the 1/3 is then equal to 25. Well, this is the cube root. What undoes cube root? Cube. So cube both sides. That's then going to be x is equal to 25 cubed, which is 15,625. Then notice that if you plug this number back in for the argument, then it would be a positive input, and that's perfectly fine. So that's our solution. Here we have 2 times log base 15 of x minus 3 minus log base 15 of 8. Since I have this 2 on the outside, I can make it a power. That's going to be log base 15 of x minus 3 squared minus log base 15 of 8 is equal to log base 15 of 2. Then I want to use more logarithm properties and try to get a single logarithm on both sides of the equation. So here I have subtraction of logs with matching bases. That means I can divide the arguments inside the logarithm. So that's going to be log base 15 of x minus 3 quantity squared divided by 8, which is then equal to log base 15 of 2. Now I have a single logarithm equal to a single logarithm with matching bases. This then is property of equality, so I get x minus 3 quantity squared divided by 8 is equal to 2. Then I can just solve this rational expression. 8 is my LCD, so multiply both sides by 8. Then this gives me x minus 3 quantity squared, which is going to be x squared minus 3x plus 9 is equal to 2 times 8 is 16. So then notice that we have a quadratic equation. So let's get everything on one side and then decide on what is our best or preferred approach. So that's x squared minus 6x plus 9 minus 16 is equal to 0. That is x squared minus 6x minus 7 is equal to 0. Then notice that this will factor as x minus 7 times x plus 1. Let's confirm. x times x is x squared, x times positive 1 is 1x, minus 7x is going to be negative 6x, and then negative 7 times 1 is negative 7. So our factorization is fine. Then we use the zero product property. That is, x is going to be equal to 7 and negative 1. Well, now we need to return back to our initial equation, and we need to see which of these work and which of them don't. Well, notice that the only situation in my original problem where I have to worry about the argument is right here. X minus 3 is the only place where a variable goes into the logarithm. So 7 minus 3 is positive 4. 7 works. It's perfectly fine. Negative 1 minus 3 would give me negative 4. So the negative argument is problematic. That is, negative 1 cannot work, and so our only solution is going to be x is equal to positive 7. Same idea here. Notice that I have log base a, log base a, log base a, log base a. So I'm going to use the properties of logarithms to combine these things. On the left-hand side, I'm going to get log base a of, well, this is subtraction of logarithms, which means that we can do division of the arguments. That's x minus 1 divided by x plus 6 is then equal to log base a of, once again, the quotient of arguments. That's going to be x minus 2 divided by x plus 3. Then, since I have log base a is equal to log base a, I can set the insides or the arguments equal to each other. That is then x minus 1 over x plus 6 is equal to x minus 2 divided by x plus 3. At this point, notice that we have one rational equal to one rational, and so this is a situation where if you so desired you could cross multiply, but that is exactly the same thing as multiplying everything by the LCD of all denominators, which are x plus 6 times x plus 3. So then that's going to be equal to x minus 1 times x plus 3 is equal to x minus 2 times x plus 6. Multiply everything out, simplify as much as possible. This is then going to give me x squared plus 3x minus x minus 3 is equal to x squared plus 6x minus 2x minus 12. That's x squared plus 2x minus 3 is equal to x squared plus 4x minus 12. Then you want to get everything on one side because I do see that this is a quadratic. But notice if I start by subtracting x squared, well then what happens? Well, the x squareds cancel out and I'm left with 2x minus 3 is equal to 4x minus 12. So now we just have a linear equation. Pick a side. I'm going to subtract 2x, and while I'm at it, I'm going to add 12 and add 12. Notice that I'm putting the variables on the right-hand side. Then I've got positive 9 is equal to 2x divided by 2 divided by 2. X is then equal to 9 halves. At this point, we should go back and we should make sure that 9 halves will work as any of these arguments. Well, 9 halves minus 1 is positive. 9 halves plus 6, positive. 9 halves minus 2, positive. 9 halves plus 3, positive. We're fine. Here we have log base 4 of x is equal to 2. So I notice that I don't have a logarithm on each side. That means I need to use the definition of logarithm and write it in terms of an exponential. That means that this is the base 4 squared is equal to x. That's the formal definition. And then we're done. 16 is equal to x. Technically we should check, but 16 is positive, and so there's no issues whatsoever. Now I have log base 2 of 5x equal to 4. Write the definition of logarithm, write it as an exponential. This is going to be the base 2 raised to the 4th power is equal to 5 times x. Then 2 to the 4th is 16, and so this is 16 is equal to 5x. Then solve for x, divide by 5, divide by 5. X is then equal to 16 fifths. We do need to check and make sure this argument will work, but 5 times 16 fifths will give me positive 16. Positive argument is what we're concerned about, and so we're perfectly fine. 2 log base 4 of x minus 9 plus log base 4 of 4 is equal to 2. Step 1, combine logarithms as much as possible. So for this first one, notice that I can write that as an exponent on the argument, so that's going to be log base 4 of x minus 9 quantity squared plus log base 4 of 4. Log base 4 of 4, we actually know what that is, right? Because this question is 4 raised to what power that's not written is 4? Well, the answer here is 1. Log base a of a is always 1. So I can just write that as plus 1 equal to 2. Well, then I need to isolate my logarithm. So this is then log base 4 of x minus 9 quantity squared. Minus 1 from both sides is going to give me 1. Well, then notice that I have a single logarithm equal to a number, so I'm going to have to use the definition. And so writing this as an exponential, that's going to be 4 to the first power is equal to x minus 9 quantity squared. At this point, notice that I have in parentheses x minus 9 squared. I'm going to take the square root of both sides. Remember that when you take the square root of a square, you do have to deal with the plus and the minus. And so this is then going to be x minus 9 is equal to plus and minus 2. Then add 9 to both sides. I get that x is equal to 9 plus or minus 2, which is going to give me that x is equal to 11 and 7. But at this point, we need to confirm what will work and what won't. Notice that the only place I need to be concerned about the argument is at x minus 9. 11 minus 9, well, that's positive 2. That's perfectly safe. 7 minus 9 is going to be a negative number, and since it's negative, I have to kick out that 7. I know that the only solution is then x is equal to 11. Log base x plus log of x plus 15. Notice that I have matching logs of base 10. So then addition of logarithms is multiplication of the arguments. So that's going to be log base 10 of x times x plus 15, which is then equal to 2. So now I can write this as an exponential equation. That's then going to be log base 10, so this is 10 squared is equal to, and I'm going to distribute the x, that's going to be x squared plus 15x. At this point, notice that we do have a quadratic, so I want to put everything on one side. That's going to be x squared plus 15x minus 100 is equal to 0. Then pick your favorite method of solving a quadratic. I'm going to factor this. X plus 20 times x minus 5 is equal to 0. Let's confirm that factorization. Negative 5 times 20 is negative 100. 20 minus 5 is positive 15, and x times x is x squared. So we're factored. Then using the zero product property, I get that x is equal to negative 20 and positive 5. At this point, we need to look back at our equation and confirm which ones work and which ones don't. Well, I need to check two places now. I need to check the argument for this first one, which is just x, and check the second one, which is x plus 15. Well, I plug in negative 20 into here, and I automatically have a problem, so negative 20 is out. Can't take logs of negative numbers. Then I have log of 5. Well, that's fine here. Let's check the other. Log of 5 plus 15 is log of positive 20, and so my solution is x is equal to 5. First, I need to get all the logarithms on the same side so that I can combine them into a single logarithm. So I'm going to subtract log base 10 of x minus 2, subtract log base 10 of x minus 2. At this point, I'm just going to shortcut because log of 2x plus 1 minus log of x minus 2, that being subtraction of logs, means it's the quotient of the arguments in the log. And so that's going to be log base 10 of 2x plus 1 divided by x minus 2 is equal to 1. Now I can write this logarithm via the definition as an exponential. That's going to be the argument 2x plus 1 over x minus 2 is equal to the base 10 raised to the first power. Then I just have a rational expression that I need to solve. I'm going to multiply both sides by the LCD of x minus 2. Then I get that 2x plus 1 is equal to 10x minus 20. Then we just solve this, minus 2x, add 20, add 20. That's going to be 21 is equal to 8x, divide by 8, then this is x is equal to 21 over 8. That won't reduce, but now we have to check and make sure that it works as arguments. So 21 eighths times 2, that's positive, plus 1 is positive, that's fine. 21 eighths minus 2, well, that's still positive, so we're perfectly fine. 21 eighths is our solution. Log base 2 of x minus 1 is equal to 5 minus log base 2 of x minus 5. Same situation, but I'm going to add log base 2 this time. Then notice that I have addition of logarithms with matching bases. That means I can multiply the arguments. That's then going to be log base 2 of x minus 5 times x minus 1, which is equal to 5. Then I can write this using the definition. That's going to be x minus 5 times x minus 1 is equal to the base 2 raised to the 5th power. I see that I'll have a quadratic. That's going to be x squared minus x minus 5x plus 5 is equal to 32. So that's x squared minus 6x plus 5 minus 32 is going to be minus 27 is equal to 0. Then we see we have a quadratic. Solve using your preferred method. I'm going to factor. So this is x minus 9 times x plus 3 is equal to 0. Let's confirm. Negative 9 times positive 3 is negative 27. Negative 9 plus 3 is negative 6, and then x times x is x squared, so we're good. Then the zero product property gives us that x is equal to positive 9 and negative 3. At this point, we need to go back and check in our arguments to make sure it works. 9 minus 1, positive. 9 minus 5, positive. 9 is fine. Negative 3 minus 1 is negative, so before we go any further, we're already done. So 9 is the only solution. As a reminder, when trying to solve exponential equations, if you can get a single base a raised to some power is equal to that same matching base a raised to a different power, you can set the powers equal and then solve like that. And just as a reminder, here are exponent rules that you might need to simplify. Then, what are our steps for solving exponential equations? First, you need to isolate the exponential term if you can. Then, at that point, you're going to take the log or natural log of both sides. Then you're going to solve for x. Now, if you can get a single base on each side where the bases are matching, then just use the equality property to save. Then just use the base exponent property. So here I have 2 raised to the x power is equal to 10. Notice that my exponential piece is isolated. It's all by itself on one side. Well, and notice that 10 can't be written as 2 raised to some power, not at least nicely. And so since this is the case, I'm going to have to take the logarithm of both sides. Now, when I do this, realize that you get the choice of the base. And so personally, I'm going to use a base that makes the most sense to me. Now, when I say makes the most sense, I see that this is base 2. Well, remember that if ever you have log base a of a raised to some exponent b, remember that that's just going to be b times log base a of a, and log base a of a is 1, and so you would just get the exponent b. What am I saying? I'm saying that here I'm going to use log base 2 on both sides. So I'm going to take log base 2 of both sides. We're not multiplying, we're taking the log base 2 of both sides. It's very similar to the way square root works. You have to take of both sides. So then I have log base 2 of 2 to the x. That's going to be x times log base 2 of 2, which is of course 1, is equal to log base 2 of 10. Well then, because log base 2 of 2 is 1, this is then of course x is equal to log base 2 of 10. Now at this point, since we need an exact solution, this is the exact solution. Great. But I also want us to get an approximation. So let's find the approximation and let's round it to 3 decimal places. Remember that your scientific calculator is not going to allow you to take log base 2 of 10, and so we're going to have to use the change of base formula, and I'm just going to use log base 10 of this. So that is log base 10 of 10 over log base 10 of 2. Well, that's going to give me 1 divided by log base 10 of 2, which I get to be approximately 3.322. So that's the approximate solution. For the next one, I have 2 times 3 to the x is equal to 12. Step 1, we need to isolate the exponential. Notice that this is the exponential. so I need to get rid of that 2 that's there. Well, what's the opposite of multiplication? Division. So I'm going to divide both sides by 2. I then get 3 to the x is equal to 6. Well, it would be nice if I could write 6 as 3 to some power, but that's not true. And so then, or at least it's not nice, so then I need to take log base 3 of both sides. So log base 3 of 3 to the x is equal to log base 3 of 6. Then my exact solution is done, because log base 3 of 3 to the x is x, which is then equal to log base 3 of 6. There's my exact solution. But if I want an approximation, remember that I need to use the change of base formula, so this is going to be log base 10 of 6 divided by log base 10 of 3, which I then get to be approximately 1.631. Next, I have e raised to the negative 0.8 times t, which is equal to 0.09. Notice that I have the exponential isolated. It's all by itself on one side. Then I just need to take the log of my choosing of both sides. Well, I see that this is base e, and since it's base e, I'm going to take the natural log of both sides. So the natural log of e to the negative 0.8t is then negative 0.8 times t times natural log of e, but the natural log of e is 1. And then that's going to be equal to the natural log of 0.09. Then we just solve for t, so I divide both sides by negative 0.8. And at this point, we get that t is equal to the natural log of 0.09 divided by negative 0.8. This is the exact solution. There it is. Now, if I want an approximation, notice that there's no need to use a change of base because I do have a natural log button on my scientific calculator. So that's the natural log of 0.09 divided by negative 0.8. Approximating to 3 decimal places, I then get that this is 3.010. For the record, I got 3.0099, but this 9 here pushes this 9 to 10, which then makes it 3.010. Continuing, same thing. I have e to the negative c is equal to 5 to the 2c. Alright, well notice that there is a problem. It would be really great if I could write them with matching bases, but e, that transcendental, and 5 don't have a nice relation. Not that is real easy to find. So what does that mean I'm going to have to do? Well, it means I'm going to have to take the log of both sides. Now, I get the choice of which base I use. Honestly, you could choose log base e, or you could use log base 5. You could use log base 10 for all I care. It doesn't really matter. It'll give you the exact same solution. But I'm going to make a base match one of these bases because I want one of them to clean up. And I'm going to say let's just do natural log, because if I take the natural log of both sides, two things are going to happen. I'm going to clear out the e, and I'll have a button that I can use on my calculator for my approximation. So then what does this give me? This gives me negative c times the natural log of e, but the natural log of e is 1, which is then equal to the natural log of 5 to the 2c, which brings the power 2c out front, times the natural log of 5. At this point, I still need to solve for c, but there's a problem. I assume that I need to divide by c because this is 2c times natural log of 5. But at this point, there is a problem. C could be 0, and because c could be 0, I cannot divide by that. So what do I need to do? I need to play a trick. And my trick is I need to add c to both sides. When I do this, I get 0 is equal to 2c times the natural log of 5 plus c. Well, at this point, what can we do? Well, the trick here is factor out a c. So then I get 0 is equal to c times 2 ln of 5, 2 natural log of 5, plus 1. Well, at this point, I've got c almost by itself, and here I can divide by 2 natural log of 5 plus 1 because that's not 0. And so when I divide by that entire thing, well, what happens? Well, then I have 0 divided by 2 natural log of 5 plus 1. Well, that gives me that c is equal to 0. Well, at this point, just to confirm that it works, why don't we throw it in there to double check? E raised to the negative 0 power is e to the 0 power, which is 1. 5 raised to the 2 times 0 power is 5 to the 0 power, which is 1. So this works. C is equal to 0. Now I have 10 to the negative 3x is equal to 28 to the x. If there was some way that I could write the bases as the same thing using some trick with exponent rules, I would, but I don't see a one. So that means that I need to take the log of both sides to get it cleaned up. So pick the log base I choose. Well, since this is base 10, I'm going to go with log base 10. In general, just if you don't want to do the change of base formula, you should probably use log base 10 or natural log. Then when you do your approximations, they'll come out nicely. At this point, I get negative 3x times log base 10 of 10. But log base 10 of 10 is 1, and so I'm not going to write it, which is then equal to x times log base 10 of 28. At this point, I need to play that same trick I did above. Because I don't know if x could or couldn't be 0, I need to add 3x to both sides. Then I get that this is 0 is equal to 3x plus x log base 10 of 28, which then I can factor out the x, so that 0 is equal to x times 3 plus log of 28. Notice that then if I divide by 3 plus log of 28 on both sides, then I get 0 divided by a real number, which is then going to be 0, and so I get that x is equal to 0. Once again, you can check your solutions for this one, but if we check them, then we get 1 is equal to 1, and we're perfectly fine.